अच्छा हो गया, बहुत अच्छा हो गया, बहुत अच्छा हो गया। हाँ।
इमिजिएट घालवून आपण
आता 2 मिनिटं झालं तरी ते नाही होत नाही. सगळे लोक मग उद्या काही काम आहे, परवा काम आहे, काही
Hello, Vaidya sir.
Yes, sir. Yes.
You are there, sir.
Yes, yes, I am.
This session is late due to some reason.
Yeah, it's okay. Shall we continue? What means?
No problem, sir. You can continue.
Okay. Okay, thank you.
So
yeah.
So, dear participant, due to some technical reasons, we are late for this session. So, for this session, again, Engineer Prasad Vaidya sir is with us. So, sir, please start your presentation.
Yes, sir. Okay, so let me share my screen.
Yes, sir.
Yeah, is it visible?
Yes, sir. Yes.
Oh, okay, fine.
Yes.
So, welcome you all for this session on time history analysis. In last session, we have seen some of the points in value engineering, and in today's session, I'm going to discuss on this how to perform time history analysis using ETAP software. Okay, so today's presentation is divided into 3 parts. First part is the classification of analysis, where we try to understand the different types of analysis like linear and non-linear based on the material, based on the analysis means input data, force, and geometry, right? And then we'll try to understand some of the important ground motion characteristics which is useful to understand before going for time history analysis. And then, of course, I will give you an start to end demo of how to perform a time history analysis on a particular building. Of course, that building is not means it's not a huge building. We'll take a small building like G+2 or G+3, and of course the model is ready with us. I will just show you how to apply this time history on the particular building. So this is the broad classification, means broad outline of today's presentation. Okay. Yeah, so the first part is a classification of analysis. So analysis is basically classified based on force, based on material, and based on deformation characteristics. So based on force, the analysis is classified as static and dynamic. The static analysis is basically analysis when your force is not varying with respect to time. So with respect to time, this force quantity remains same. So that is called as a static analysis. The dynamic analysis is the one when your force is varying with respect to time, like your time history. In time history analysis, the force, that is your acceleration force or maybe velocity or displacement, that varies with the help with time. So that is a dynamic analysis. Material wise, it can be classified as linear and non-linear. The linear analysis is the one when your force and deformation is linear up to certain point. That is called as point of proportionality, where Hooke's law is obeyed, stress and strain are proportional, and after that your non-linearity will start. The nonlinear behavior will start from the point where the first crack in the material will develop, and from that point onward, your analysis is classified as nonlinear analysis. It will be a nonlinear analysis in that case. And then deformation wise, of course, it is a small deformation analysis and large deformation analysis. The small deformation analysis, we will consider the material nonlinearity as well as geometrical, only material nonlinearity is considered. And in large deformation analysis, both material and geometric nonlinearity is considered. For example, P delta analysis, buckling analysis, these are the examples of large deformation analysis. In small deformation analysis, the material is means member is cracking, it is deflecting, but it is not collapsing, right? So the most difficult part out of all these analysis is last one, which is your large deformation analysis, where you will consider material as well as geometric nonlinearities simultaneously in your model. As far as this ETAB is concerned, the ETABs considers the material nonlinearity in link element. So limited material nonlinearity is there, but large deformation analysis where geometric as well as the material nonlinearity is concerned, that cannot be performed using ETAB software. Some other softwares are also available. And again, you should remember that in ETABS, the material nonlinearity is limited in link element. So whenever you are going to use link element, then only this nonlinearity is considered. For example, if you are doing, say, base isolation type building, okay, where the isolators are modeled with the help of link element, and then this link element is a nonlinear element, then only you can go for time history, nonlinear time history analysis. Otherwise, it is always linear, because the nonlinearity is concentrated in link element only. So other examples are, maybe isolator is one of the example, maybe tune mass damper, where you use a link element to model the damper. That will be the another example. Sometimes you need to model a gap type behavior, that means pounding type behavior. So gap element is used. That is also a non-linear element. So all dampers, including friction dampers, maybe your tune mass dampers, where you need to use the link element, there only you can consider the non-linearity. That is in material non-linearity. And simultaneously, both material as well as geometric non-linearity is not considered, right? So that is about the ETAB. Okay, so this is the basic classification of the analysis. Now there can be a combination also, force based and material based. So your analysis can be static linear analysis, or it can be dynamic linear analysis. Okay, so force is dynamic, but material behavior is linear. So dynamic linear analysis, dynamic non-linear analysis is also possible, right? So like that, there may be a combination. So you can classify your analysis accordingly, and then only you can choose the correct type of analysis applicable for your engineering problem, and then go for that particular analysis. Now we will be dealing with linear and non-linear analysis, but whenever there is a link element only, then only you can go for non-linear analysis, like time history, non-linear modal time history analysis, like that. Okay, so this is the basic classification of analysis. Now what we are doing actually is we are applying a force on the material. The force can be static or dynamic. As we see, the force can be in the form of loads, vibrations, settlement, or thermal changes. So that is your excitation, which is applied to a particular structure, and the structure can be elastic or inelastic. Sometimes it is elastic, or it may be inelastic. And then we are predicting the response to that particular load in the form of displacement, strain, stress, and stress resultants. So response can be linear and non-linear. So this is a basic procedure of your analysis, where the force is there, which is static or dynamic, where the structure is there, which is elastic or inelastic, and then out of that, your response can be linear or non-linear. Okay. Now we'll try to understand the basic ground motion characteristics first. Okay, so seismic waves are classified into 4 types, as you know. First is P wave, S waves, love waves, and release waves. Now, you should understand the difference between these 4 types of waves. You can see this first waves is like a compression, which will induce the compression into the soil. There is no deformation of the mass. The soil mass is not getting deformed. So there is only compression. So it will travel like this. So you can see this closely spaced lines here. So this represent compression, but along this line, axial compression, right? So it will travel like this. This is called as a P waves. S waves, you have got the entire mass of the soil, which is deforming. Okay, so that is the most dangerous waves, S waves. Release waves is similar to this. The only difference is some top layer of the soil is getting dispersed, other layer is as it is, and then of course another waves is low waves. So this is how this waves are traveling through the soil mass, and it will reach to your building. Now, as far as this parameters are concerned, so you have got a building somewhere here. So there is somewhere inside the ground, there is a source of earthquake where the actual earthquake energy is produced. And then if you project that point on the surface of the earth, that is called as a epicenter. And from that point to your recording station, where your recording station is situated, that distance is called as a epicenter distance. So this epicenter distance can be in kilometers, and then based on this epicenter distance, you can classify your earthquake as a near field earthquake or far field earthquake, right? So if your epicenter distance is less than a 15 kilometer, then that is categorized as a near field earthquake, and if it is more than 15 kilometer, that is far field earthquake. Of course, both of the cases, near field or far field, the response of the structure is different. Okay, and then your building is situated somewhere on this particular map, and then this building will receive the seismic waves, right? And where recording is at different point, the source is at different point, and then of course the epicenter is a different point. So these 3 points are there, and along with the building. So we need to correlate all this data to get the response. Okay, so that is the basics of your seismic waves. Then as far as this recording is concerned, now you know that this building will vibrate in all 3 directions. So X direction, Y direction, and Z direction, because you have got the entire weight of the building. So the Z direction seismic waves may not be damaging, because the effect is mostly counterbalanced with the help of the weight of the structure. Whereas X and Y direction, you need to take care of these forces, X and Y direction, and that's why we mostly design our building for X and Y direction earthquake, that is horizontal earthquake. Vertical effect is sometimes, in most of the cases, it is not predominant. Whereas, but IS 1893 2016 says you need to consider the vertical earthquake effect when your structure is located in zone 4 or 5, which is high seismic zone, where the structure has vertical or plan irregularities. So when your structure is irregular structure, that time also you have to go for vertical earthquake acceleration. The structure is resting on soft soil for bridges, structure has long span, or structure has large horizontal overhangs. In all these cases, you need to go for the vertical earthquake effect also. So ground motion recording equipment will something like this. It will look like this, and then what you get the record will be like this. Okay, so it is nothing but a time versus your quantity. Now this quantity can be acceleration, it can be displacement, or it can be velocity, or whatever record will be there. You can produce any record, but most of the cases this acceleration is recorded versus time. So time versus acceleration, if you plot on this particular scale, you will get a graph, and that is nothing but your time history, right? And it has got the units, particular unit, maybe in centimeter per second per second, or meter per second per second. So it is dependent on the recording. Okay, so ground motion can be recorded in terms of ground displacement, velocity, or acceleration. Modern strong motion accelerographs are designed to record three-dimensional components of ground acceleration. Now there are three dimensions, as you know, X, Y, and Z. All three-dimension components can be recorded with the help of this equipment. So that is your ground motion record. Okay. Now there is an interesting fact about earthquake magnitude. So each of the magnitude is generally basically 33 times more powerful than the last magnitude. So this is very interesting. So if you compare between 6 and 7 magnitude, the difference in amount of energy release is around 33 times. So likewise, if you compare the magnitude of 6 with magnitude of 8, there will be around 1089 times difference in energy. And if you compare between 9 and 6, it is around 35,937 times difference. Okay, so ninth magnitude earthquake is around 36,000 times more powerful than 6 magnitude earthquake. Okay, so that is a very interesting fact about magnitude. So each of the magnitude is basically 33 times more powerful than last one. Okay, then there is a term called peak ground acceleration, which we call it as a PGA.
What happened, sir? Hello, sir. Prasad, sir. Hello, Prasad, sir. Hello, Prasad, sir. Prasad, sir, I think lost their network. I think Prasad, sir, lost their network, sir.
Okay, I will call him.
Yeah.
Please wait for some time. Internet connection at speaker side was get stopped. काही तुम्ही लॉग इन करा ना, पुन्हा जॉईन करा ना, मीटिंग चालू आहे. येस येस येस, आले 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 आले. येस सर.
Hello.
Hi, sir.
Okay, I think there is a connection
Network
issue. Yeah, network issue. Anyway, I will just share my screen again. Yeah.
Yes. Yes.
Okay, so I'm talking about response history. So once you apply a load in the form of time history, you will get a response in the form of, again, in the form of history. And that is called as a time history response, right? So response is also in the form of history. So the response can be in the form of displacement, force, velocity, or maybe sometimes base shear, whatever. But again, it will be a history. Okay, now now we'll try to understand. There are two methods of time history analysis in ETAB. One is called as a direct integration method, and another one is modal time history method. Okay, so direct integration method and modal, we will try to understand what is the difference between these two methods of performing the time history. The first method is always a time consuming, but it will give you an accurate results. For example, this method, direct time history method, direct integration method, will solve your dynamic equilibrium equation for each of the time steps. So you know this dynamic equilibrium equation where mu double dot plus cu dot plus ku equal to f of t. So that is your force. So it is basically like this. So you have got a moving mass. So moving mass will generate an inertia force. So this inertia force, whatever inertia force is generated due to the moving mass, that is resisted by the two forces. One is your elastic force of lateral load resisting element like columns and shear wall, and another is a damping force which removes the energy from vibrating, right? So this is how this dynamic equilibrium equation will be there, and this equation is solved for each of the step in direct integration method. So analysis involve integration of structural properties and behavior at series of time steps. So if you perform, let us say, 1000 time steps of 0.002 each time step. So for every time step, whatever the number of steps will be there, for that every time steps, this equation is solved. So that is direct integration method. But this will give you the accurate result but of course your solvers will be strong in that case, and it will of course take more time compared to the modal time history. Now the another method is a modal time history method, where actually the response of the mode at each of the level is combined to get the final response. For example, say if you have got four modes, mode 1, 2, 3. Suppose there are three modes, and then if you want to combine the response of all these three mode, so you need to find out the deformation at this level, at which time and at what quantity this deformation will be there. So that is this equation: u is equal to phi into q. So this is phi, which will give you location. Suppose if it has top level, so that will be the top, and q is the time. So response of each of the mode with their participation ratio is combined to get the final response. So this procedure is repeated for all levels, and then the final deformation shape is decided. So this depends on how many number of modes is considered in the analysis. If you consider the more number of modes, your analysis will be accurate. But generally, first three mode will give you the response of the particular structure. So first three modes are always important. So it is like this. So this say this U1 and U2 and U3 are the responses of each of the mode at each of the level. So phi 1, phi 2, phi 3 are the deformation at the levels, and then you can combine this to get the net response at particular level. So along with the participation factor, so participation factor is also important. Supposing if you are mode 1, like you can see here, this mode 1, this deformation shape is more towards last mode, right? Third mode. Okay, why? Because this may be having more participation. So whatever the mode is having more participation, your final response will be towards that particular mode, right? So participation is also important. So that is called as a modal time history. Okay, so there are two methods. One is direct integration and another is modal time history. Now in time history also, the modal analysis can be performed with the help of Ritz vector or eigenvector. Right now, what is the difference between these two? So most of the cases, this Ritz vector is recommended over the eigenvector analysis. Why? Because this Ritz vector will capture the mode first having more participation. For example, let us say if you have got a building and then there is a small antenna over the building, or maybe some tower, and this is very slender compared to your building. The mass of the building is huge, whereas the antenna mass is very less compared to this building. Now if you apply horizontal acceleration to this particular building, what will happen? This particular element which is at the top of the building, because it is very slender and the mass is also less, it will oscillate in all in that particular direction. And modal, the participation for this particular element is very less compared to the building, because the building has got large mass, whereas only 5-10% mass, not only 5-10%, less than that mass is participating in the vibration of this particular element. So ultimately, once you combine this mode, what I expect is our final response is towards this large mass building, not towards this. Otherwise, it will give you large time period. And that is not happening in case of eigenvector. So once you use the Ritz vector, what it will do, the modes which will be having higher mass, that will be captured first, and then the modes which will be having less mass will be captured, right? So that's why this Ritz vector is recommended over eigenvector. Similarly, when you have got mezzanine floor in the building, and mezzanine, because it is a small floor, so it start vibrating, and if you apply a vertical acceleration to this particular building, so this particular element will vibrate because it is slender. So the what you want is the entire response of this particular building, and that is possible only in case of Ritz vector, not in the case of eigenvector. So there are two methods or two choices: either you can perform Ritz vector or you can perform eigenvector. But for response spectra and time history analysis, Ritz vector will always give you accurate results. Okay. Then the time history can be periodic or it can be transient. Periodic means you can repeat that particular history for certain period of time, and then following that you can apply another history. So it can be a periodic, like one history after another history, or it can be transient, only one history will be there. So this is the one. Okay. Then the next very important thing is time history data. So what you get is time history data will look like this. So this is a Butch earthquake data, and then we need to understand each and every quantity in this particular data first before applying it to the structural model. Okay, so first you will get the name of that particular earthquake. Now here it is Butch earthquake, and then the date, then time instance, and then you will get the magnitude. There are two actually magnitudes. One is the surface magnitude and another is body wave magnitude. So you can see here 7.0 MB is written here. So MB is means body wave magnitude, and 7.6 is MS. MS means surface wave magnitude, right? So two magnitudes will be mentioned. Then you have got the location of the station where this earthquake is recorded, in terms of latitude and longitude. So these are the coordinates of that particular station. So you can get why this is important is because to calculate the epicenter distance. So with the help of this data you can calculate the distance, epicenter distance, and then you can decide whether it is far field earthquake or near field earthquake. And then of course the component of the earthquake is there, northeast component. So this will give you the direction of that particular event. Then there is a term called Exclogram bandpass filter. Between some frequencies mentioned 0.07 hertz to 27 hertz. So what does it mean is sometimes when there is recording, when the recording is going on, there are certain other movements also. For example, vehicular movement nearby. Okay, so we don't want that particular activity to be captured in our record. So what we want is this movement frequency is very less compared to the earthquake frequency. So we will filter our data between that particular frequency. So whatever the vibrations are there below 0.07 hertz frequency, that is not recorded. So after 0.07 hertz to 27 hertz, whatever the movement or vibration is there, that is only recorded. So that's why this filtration is important. Then you have got the initial velocity, initial displacement of the structure at that particular instant. And then as I told you, this peak acceleration value is mentioned in meter per second per second. Now this unit is very important because ultimately when you input your data into the ETF file, you need to put the scale factor, and that scale factor depends upon your input unit, means recording unit of your time histories. Now here you can see the recording unit is in meter per second square. So this recording unit is very important. Sometimes it is a centimeter per second square. So accordingly you need to convert it with the help of scale factor. Now then there is a number of acceleration points. So 26,706 acceleration point data is recorded with the interval of 0.005 second. So total earthquake is recorded for 46.94 second, and each point is recorded with the interval of 0.005 seconds. So first point is at 0, then 0.005, then 0.10, like that. So it goes on increasing like that. So there like that there are 26,706 acceleration point. So if you multiply it 26,706 multiplied by 0.005, you will get this value. So that is 46.94. So that is your total time of record, right? No, that is this peak acceleration value, but total time is 26,706 multiplied by 0.005. That may be around 133 or 134 second. So that is the total time of recording. Okay, so that is how this time history record will look like. Now sometimes this record you have to means for software application you have to make it a notepad file for this record, and then whenever sometimes it is in your decimal points like this, or sometimes it is in scientific record. So that you need to convert into the quantities like this to so that the computer can read your time history record. So that is about the time history record. Now I will go to the actual model and I will show you how this time history is applied to a particular model. Okay, so let me share my file. So I will share my screen with you again. Yeah, is it visible now? ETAP's screen? Okay, okay, fine. So this is one of the model that is prepared now. This is one of the G+3 building where cantilevers are there on all sides, some columns are there, and then releases. Shear wall is there in between. So I will try to apply a time history to this particular model, and I will show you how this time history is applied. Before that, I will just show you the file, time history file, how it look like, and then we'll go ahead. Okay, so let me open my file again. Yeah. Okay. Can you see this file now?
It is visible.
Yes. So this is a notepad file for the Butch time history record. As I shown you, the same file is here, but that is a notepad file, and you can see there are number of points which is recorded. The points are around 26,706 acceleration points with a interval of 0.005. Okay, so there are certain things you need to note down. So in this particular file, the first thing is how many number of columns are there. So 1, 2, 3, 4, 5, 6, 7, and 8. So 8 columns are there, so that the software can read the data like this. You have to tell the software that there are 8 columns in the file, so you read accordingly. And then how many lines from where the software should start the reading the data, that also you have to note down. For example, there are this first line, second, third, fourth, fifth, seventh, sixth, and seventh. So you don't want to read all this data, which is just for the information, the topmost data. Okay, so you should start reading from the 8th line onward. So there are 8 columns, and you should start your reading the data from 8th line, right? So that is very important. The next important thing is, as I told you, the unit of measurement. Here it is meter per second, right? So meter per second square is the correct unit of measurement. So all these points is very important before going for the history record. Okay, now I will show you how to apply this history to the into the ETAP model. Okay, so let's share it again. Okay, so first step is to define the function. Okay, so here there is a tab called function. So if you go to the function and then just choose time history function. Okay, now this is already defined. I will just delete these functions so that you can understand it, how to define it again. So you will find function like this. So here you have to choose what type of function is applied. So just choose from file, because we are using a function from file, and say add new function. Okay, and then put the name of that particular function. Let us say it is Butch earthquake. So I will just write Butch, and then I will put the date. Okay, date 12/2020. Whatever name you can give, there is no issue. So Butch earthquake. Then give the path of that particular file here. So this is my notepad file. Say open. So now the important thing is this values are recorded at an interval of 0.005. So put here 0.005, right? Okay, so values at equal interval of 0.005. Okay, and here the name of the file is Butch. I will just put the date 2020, right? And then header lines to skip. As I told you, there are 7 lines which the software should not read, and after 7th line, the reading should start. Okay, so the header lines to skip will be 7, right? And the number of points per line is 8. Okay, so once you click on that, you will get a graph like this. You can see here the graph is generated. So this is nothing but your time history record. You can see here the last time will be around 133 134 second. That you can check. 26,706 multiplied by 0.005, that should be around 133 134, correct? So that is the last recording point. Okay, so your history graph will be displayed here. So now this function is defined, and just say okay for this particular function. It will take time. Yes, now you can see this history function is added into your particular data. So Booch 0 to 12 2020. So that is the function name. Okay, and just say okay. Now the function definition is over. Now what you need to do is you need to define the modal load case. Now, as I told you, there are two options in the modal load case. One is your Ritz vector analysis and another is eigenvector analysis, right? So where to define that is, if you go to define, and here you can see the modal case. Okay, so if you open it, now it is already a Ritz vector which is defined, but I will just delete, or you can modify this case so that I can show you. Okay, so here you have to choose the option. By default, it is eigenvector. So you have to convert it into the Ritz vector, and whatever the loads which is used in the time history analysis, that you have to apply in this particular Ritz vector. For example, I am going to use UX and UI acceleration load. That's why UX and UI is added in the Ritz vector analysis. Okay, and then other data you keep it as a default one. Don't change anything. So mass source, of course, you need the mass source is already defined. So mass source is nothing but the total dead load plus portion of the live load, that is already defined. Okay, so other data you keep it same. So that is your modal load case setting, and just say okay. So now this modal Ritz vector case is set. Say okay. The third step is to define the time history data. Okay, time history load case. So again, you have to go to define, go to load cases, and here I will just delete this case and again assign one more case. Okay, so these are the cases which is already defined. The first is dead load case, another is live load case, then roof live load, then EQX and EQI. These are the static load cases for earthquake. RSX and RXY are the response cases, response spectra cases for earthquake. Now I am going to add the time history case in the same model. In the same model, you can add number of cases. That is, there is no issue at all. So you can add your static load cases, response spectra load cases, time history cases, different time history cases. For example, if you want to use 3 different time histories, all 3 can be added in single model. There is no issue at all. Okay, so you can add a new case, say add new case here, and here you have to write down the name of the case. Let us say time history in X direction, TSX. Okay, now the type of the load is time history, and once you select the type of the load, he will ask you whether it is linear modal time history, non-linear modal time history, linear direct integration, or non-linear direct integration time history. As I told you, this non-linear thing will only work when you have got link element in your model. So we don't have any link element. So right now I will keep this linear and modal. Direct integration also you can perform, linear direct integration, but the thing is direct integration will take time. It will take around 1 hour or 2 hours to run your analysis. So for this particular model, I am preferring this linear modal time history. And then you have to say add. Now I'm going to add the load. So load pattern is my acceleration load, and it is in u1 direction because the time history is in x direction. So u1, and then choose the function which is your Butch earthquake function, right, which is already defined. Now this scale factor is important. Now what type of scale factor is to be used is that depends on the recording unit. As I shown you, the recording unit is in meter per second square, and your current ETAP unit is per second square. So your scale factor should convert meter to So that is equal to 1000, correct? So it depends on the recording unit and current ETAP unit. Current ETAP unit you can find out here. Here, if you open it, you will get the current ETAP unit. So I am putting the scale factor equal to 1000 because I need to convert meter into correct? So that is 1000. Now modal case is reads. Now whether it is a transient or periodic time history, it is transient time history. We are not using periodic. Now the most important thing is number of output time steps. This is different than your actual time history record. Okay, so you should not confuse with the number of output time steps with the time history record. Now here it is output time steps, so it should be carefully selected. So how to select that number of output time step and time step size? There is a the important thing is you should not miss any peak acceleration value. So if there are peak acceleration at some of the time instances, you should not miss it. That is the one reference that I can give you to select the time step size. The another one is there is a formula to calculate the number of time step size. So for example, if you have got, say, for this time Bush time history 26,706 acceleration points are there with an interval of 0.005. So that is around roughly 134 second, roughly 134 seconds. So you add in that particular 134 second 5 times your modal time period, first modal time period. So let us say if it is 1.2, so 1.2 into 5, so that is whatever the quantity is it that you add into your this, and that is your total analysis time, and that divided by output time step will give you the number of time steps, correct? So for this particular instant, I will just keep this 6700 as a number of outputs time steps, and each time step is 0.002, correct? So that you have to work out properly, okay, for any of the time history. For this time history, I'm just keeping this random data as 6700 time steps of 0.002 each time steps, okay, and just say okay. So now this model time history case is defined, just say okay, and then your model is now ready for analysis. Now you likewise you can create number of time history cases in the single model. Okay, so there is no issue at all. Okay, so let's run this analysis, and then we'll try to interpret it, the result of your time history data. Okay. It will take some time to run. Now for every time step you will get the one response value. Okay, so after running I will show you how to check this response values for every time steps. Okay, so this is the deformed shape of your building. Now I will just check the deformed shape for the time history case. Okay, so here you go to the time history, and once you select the time history, he will ask you at which time you want response. Now if you change this time, you can see that at every 0.002 second you have got the result. Okay, so likewise any time step you can select, you will get the result of that particular time step. Now I'm just refreshing it. So that is the deformation shape. You can see we have put 6,700 time steps. So out of that, this 43 time step results are this. Okay, so likewise, you can get the history of any of the time step for any of the response quantity. For example, the response quantity can be deformation for any node. For example, if you choose this a single node and if you want to find out the time history of this particular node, displacement time history of the node, that is possible. So what you will get is 6,700 results. Okay, 6,700 result of displacement for single node. It may be positive, it may be negative. Similarly, if you find out, let us say the base shear value, you will get 6,700 base shear values for each of the time steps, right? So likewise, you can calculate any response. And then there are graphs which is ready-made, readily available. So if you go to display and then show plot function, you will get these graphs which is readily available. You can plot your quantities with the help of this graph. So you can select your quantity. Right now it is base shear which is selected. So you can see the variation of base shear. It is 10 to the power 9. Remember, it is 10 to the power 9. So maximum is around zero point 0.8 into 10 to the power 9 kilonewton is the maximum base shear which is generated in this particular time history, right? So you can change this function from here. If you don't want this base shear, you want other quantities, all these quantities are available. For example, shear force, input load, joint velocity, joint displacement, joint reaction, joint acceleration, column force, beam force, energy, base force, and wall force. All these quantities you can plot. You can change this x and y parameters also. If you want that I want time to be on y-axis, then you can interchange this also. That is also possible. And of course, this whatever the data is there, that you can export to the Excel. So if you click on this particular thing, you will get the data. Not here. If you click on this particular thing, you will get the report, summary report like this. Okay, and then if you want the detailed report or in the formatted data, so that is your data. Okay, so these are the time period values, and then with respect to time period, your acceleration or base shear values in the form of 10 to the power 9, correct? So that's it for the time history. So you can check this result, but the important thing is whenever you go for actual analysis, you should always perform minimum 3 time history, and then you can get the output for further processing like design and all. Okay, so minimum 3 time histories are required. More than that is always welcome. So minimum 3 time histories you have to perform to go for the designing. Okay, thank you very much. That's all from my side today. Now we can open the question and answers.
Dear participants, if you are having some question, then you can type in the chat box, or you can unmute yourself for a while, and you can directly ask the question to the expert. So there is rather feedback from the participant. Thank you, Disha Shaha. Sir, I think
yes, questions are not there, I think.
yeah. So you can just sir, the website, do you know there where from we can download this time history data and all that? You can share in the chat box.
Actually, if you Google it, you will get that strong motion record site. There are certain Indian sites are also there. Foreign strong motion record sites are also there. Just you Google it, you will get it. Strong motion, yeah, strong motion record. If you search like that, you will get that strong motion record. but that is not filtered, or you need to prepare properly for your input file as a ETAP. So that is just the raw data. You will get it from the site, and then of course you have to arrange it as per your requirement. Like it should be in the notepad file first, then it should not be a scientific digits. Okay,
Yeah.
so you have to arrange it like decimals and all. So that you have to do manually. But the data you will get it from site. There are certain sites, if you Google it, you will get it. I don't remember the exact name of the sites, but Google.
Shubham
Yes.
Kolle is asking that how to check the model mass participation.
Modal mass
Model mass
participation.
participation, yes.
Modal mass. Okay, I will show you how to check the modal mass participation. For that, I will just share my screen and then I will show you where to get the modal mass participation. Yes, can you see the screen now?
Yes, sir.
Okay, so there is an option called display show tables, right? So if you go to show table, you just open analysis, and here you will get the results, and then in results you will get the modal result. Okay, can you see this now? And here there
Yes,
is an
sir.
option called modal participating mass
Mass
ratios.
ratios. Yes.
Okay, if you tick this and just say okay, you will get this table. Okay, so this table is nothing but your modal mass participation ratio. Yes. Okay, can you see this now?
Yes, sir. Yes, sir.
Yes, so this is how you will get this modal participating mass ratios. Yes. Okay. Okay. Yes.
Another question was there. What stage 90% mass should
Hmm.
be received? So that you have to check from that record.
Hmm. What is the question? What?
At what stage 90% mass should be achieved?
Yeah, actually, this depends on your building configuration. So that is, it is possible that you will get the 90% participation in the third mode itself, or you may require more than 30-40 modes to get 90% mass participation. Okay, so you have to check in that particular record how much is the mass participation at which mode. If it is there in the first three mode, well and good. So the maximum mass should participate in first 1, 2, and 3 mode. That should be good for your model, right? And if it is not participating, then what you need to do is you need to increase the number of modes to get at least 90% participation. So some should be at least 90%. Yes.
So thank you, sir, for this wonderful session, hands-on session. Because of some busy schedule, I was unable to start this meeting at exact time because it was one of the crucial meeting as HOD.
Yes, yes.
So I have started it a little bit late. But it was nice to see again that time history analysis, how we can carry out in ETAP software.
Yes.
So I also thanks to all the participants for being with us with this session. And again, tomorrow morning, we will be meeting with this next session in this Sttp at 9:30 a.m. Thank you, Vaidya sir, once again.
Yes, sir.
And in few minutes, we will end this meeting here. If any participant was remaining, then you can add your mobile number here as attendance. And then we will close this session today here now.
Yes, thank you, Khandve sir. Thank you
sir.
for this. Yes, yeah. Thank you for giving me such a wonderful platform again. Okay, thank you very much. Thank you.
Yes, sir. Yes, sir.